And that's good. Okay, so welcome everyone. So just as a very quick introduction before we get on to the talks, obviously today we'll have, we're covering FPGAs, and we have talks from Giovanni Punzi and Thomas James on applications of these devices to LHCb and CMS. So just some brief news, which is purely to advertise our next meeting of the forum, which will be on Wednesday, the 8th of December. It's linked there in the slides, or so you can go to the Indico. We'll have two talks there. The first on the VecMem library, and the second on GPU developments in the CERN Beams department. So we'll look forward to seeing you there. We're also starting to plan a program of meetings for 2022. So as ever, feel free to contact us at the email address below with any interesting topics, either that you'd like to present yourself or that you'd like to see us cover in that program. So without further ado, let's move on to the actual talks. So first of all, we have Giovanni Punzi from Pisa, who will talk to us about FPGAs and LHCb. So over to you, Giovanni.
Hi. Okay, thanks for inviting me. Let me try to share. And okay. Okay, let me see if I can have this full screen. Okay. Okay. Can you see this?
Yep, that's all good.
Okay. Okay, can I start?
Yes, please go ahead.
Okay, so thanks for having me here. I'm going to talk about the kind of experience we are having now in LHCb with accelerating the reconstruction with some custom computing architecture implemented in FPGAs. And I have an unavoidable piece of introduction that I have to make to explain why we have a motivation to do this. This is a nice plot that shows a history of event size and trigger rate, well, let's say level 1 rate in number of experiments. And there has been a clear trend of ever increasing power that is being used to do these things in, let me do this so it's easier. So in doing these things over time, and has been mainly propelled forward by the use of commercial CPUs, most of these things. Now things are becoming a little bit different, partly because of the way the evolution of Moore's law is going, but also partly because of the physics that is becoming more and more on the side of precision measurements. And so we have this increasing need for specialized computing that makes the approach of heterogeneous computing more and more attractive as we move forward. And one specific thing I want to say regarding LHCb is that, as you can see in this plot, LHCb is in a particular region where you have a high rate of events at the smaller size. And with run 3, we are actually moving off the chart in this plot. We are now going to really high rate at the point that we have the rate of the full rate of the LHC going into our processing. So we run events and we have to reconstruct events at 40 megahertz essentially. Okay, so this motivated a significant change in the DAQ model in run 3. In the upgrade, we now have a real-time analysis approach to the data. There is very little happening offline, and most of the reconstruction has to happen online with very high quality. And we write a large rate of events, sometimes with reduced information, in which we call turbo, but we certainly have to process a huge amount of events in real time. And so we have a large computing power deployed in the form of CPUs and GPUs split into stages with a large buffer in between the two stages we call HLT1 and HLT2 in order to do some calibration and alignment. This is a significant challenge, and the fact that LHCb is smaller than other experiments should not be should not be a reason to think that it's a small job, because having a low PT threshold means that the amount of data that you have to deal with, the number of tracks, is not too different from what you have in general purpose central geometry experiment. Okay, and of course, it's going to be even more difficult as we go to the LHCb upgrade too. So one idea to face this large amount of reconstruction that you have to do is to push the reconstruction to earlier and earlier levels in the DIQ. And in particular, what we are addressing here today is what reconstruction we can do even at the pre-build level. So before data actually enters the event builder, which is usually a place where we do only very limited processing, we are trying to have more intelligent bit there. Of course, this is a difficult place to be because we have 30 megahertz event rate on the average, and we have very little space for doing buffering or time multiplexing. There is, though, an advantage of working at this stage because you can exploit the modularity. You can just look at the pieces of the detector that interest you in a particular moment. You don't need to unpack the whole event. You even have a chance of reducing a little bit of the flow of data. And it can be done in a way that doesn't disturb anything else in some way, because you do things as they happen during the readout in an almost transparent way, provided you can actually do this. And FPGAs have proved to be essentially the ideal device for doing processing at this level. You probably know that they are promising for a very large number of reasons. There is a very large I/O capabilities. Sometimes you can do terabits per second, large internal bandwidth. You can have computing resources distributed over these chips. You have DSP and other things. You have low power consumption. It's very flexible. It's easy to do very, completely custom things. And they are still improving with time in a significant way, and they also highly reliable devices. That's, of course, this is been exploited also outside the HEP, and it's well known that when there are complex projects that don't need mass production, usually FPGAs find a very good use. And I have looked for various examples, I said, outside our field in vision, military, or other type of applications. And we see that the use of FPGA has been capable of bringing factors of speed up that are quite significant, of tens or hundreds of times what you can obtain in other ways. And this encouraged us to explore this also in HEP to the maximum extent that we could. So in order to actually use this, you need also some to take care of the architecture that you use. It's not just the device. We went for implementing the greatest amount of parallelism we could, and so we used this custom architecture for computing that we call the Retina architecture, where there is a large switch which has a very high bandwidth that delivers data to a large number of individual cells that are active engines that perform computation at the local place, and each of them is assigned a specific region in the space of the parameters of the track of the object needs to be reconstructed, so that they can independently look only for the hits that are in the vicinity of a particular region of the parameters of the tracks and check whether there is a track, and they get some analog excitation that is similar to what you get with the neuron, with actual neuron. And so in the space of the parameters, like you can see in this representation here in this plot, you find clusters of excitation of these cells that tells you where there is a track. Okay, so in order to use this effectively, you have to do a lot of programming FPGA at a low level in order to do this efficiently, but we already had the projects in R&D that demonstrated that this is possible in prototypes, and it actually works at the desired speed. But applying this in an experiment is clearly a different thing. You have to face many more questions, starting from integration within the DIQ. In a DIQ like that of LHCb, you cannot easily have a large monolithic device. So we had to split this kind of computation in a number of different boards. So our approach is to pair each readout board in the DIQ with a tracking board that is connected to that. Each of them performs some processing and then produces with very low latency some amount of reconstructed data like tracks, and does this so quickly that it can be added to the raw data block. Essentially, you have a process that produces some reconstructed data that it's invisible to the rest of the DIQ. It just looks like there is an additional detector producing extra data. This is actually tracks. Okay, so in order for this trick to work, of course, you not only need fast boards, but you need to find a way to have them work all together. And so we have to find a way to connect them, and we use this system of fast optical links in order to make them work as if they were on a single device. This is actually works well because we now have a very low latency connections, and it has also been demonstrated. It's a kind of architecture that is similar to what has been done in other contexts. For instance, Microsoft did this kind of arrangement in order to do acceleration of their cloud computing with an array of FPGA that operates like if it were a single device. So this is kind of similar, but it's done at different speed. So in order to have a real case to apply this thing, we have taken we have taken a specific detector in LHCb. We have been tackling the Velo reconstruction. This is currently being performed in HLT1, and we are now looking at the possibility of doing this even before building. Now, I show here just a plot to give you an idea why we have chosen this particular detector. This plot was actually done for CPU processing, which is now obsolete since this has been moved to GPU now. But I only use this for qualitative purposes, and it's actually much clearer and much easier to understand that the profiling that you see for the GPUs. My only point is to show that there is a certain amount of computing power that is needed to reconstruct each of those sub-detectors in LHCb, but the Velo is quite a big chunk of this, in spite of this being only about 10% of the data on the detector. It's intrinsically more intensive, and this is the reason why we chose this as a way to have a small flow of data that allows us to build prototypes with a small number of boards, but still to have a quite hard problem to solve. So this has been taken as a test case. We are not going probably to match all the performance of the current system, but it's an R&D project that is part of an initiative in LHCb, which is called the coprocessor test bed. There is a system that has been designed with the purpose of trying and test new processing technologies live during run 3, so we can experiment with them in a realistic environment. So the first step of the reconstruction of the Velo is to actually find the clusters of pixels. This is a pixel detector, and you need a non-trivial 2D cluster finding in order to proceed with the next stage of the reconstruction. Okay, so we have tackled this with an approach similar to the one that I showed you before to find tracks. That is, again, we have a system of cells that this time are cells in the detector space, and they are independently active and only talk to their nearest neighbors in order to get an agreement of whether there is a cluster in that position. In principle, this sounds simple. In reality, it's more complicated by the fact that there is a large number of pixels in the Velo detector. There are actually tens of millions of pixels, and it would be too expensive to implement all these metrics for the whole detector. So we had to use a more clever scheme in which we have a representation that I would say it's kind of a sparse matrix representation of this data. We have data that comes in through sequential lines, and then there is a piece of the FPGA which is allocated dynamically with some parts of the detector in order to contain only the regions of the detector where there is actual data in that particular event. So we devised this kind of systems that can do all of this on the fly while data are coming in without stopping the flow. And then at the end of each event, we find all these small matrices, and we push all the data out in parallel, and then they are serialized for the output, of course, so that we can immediately take on the following event. This thing took some time to devise, but it's actually very effective in terms of parallelism and not having to wait. And in fact, we also simulated this in detail, and we were able to find that the performance of this kind of reconstruction are very good, are very much similar to what you get from a full software cluster finding. So you see plots that show you the resolution between the reconstructed heat and the generated heat, and the plots of the efficiency of single clusters, but more importantly, the effect of the efficiency on the reconstructed tracks in LHCb, both from just standalone velo tracks and on more complete long tracks that traverse various detectors. And we could find out that it is actually possible, this algorithm, to have a tracking performance. This is barely distinguishable from what you get from full software reconstruction. So we proceed to actually implement this in prototypes, and we coded all this firmware directly in the HDL and implemented the first test on Xilinx 5 FPGA. So with 350 MHz clocks, we are able to actually process realistic events at 2×10⁻³ with the speed that exceeds 30 MHz. Is actually more than closer to 40 MHz. And so this shows that this is actually something that you can do at these speeds. I'm seeing this is the speed not of processing single clusters. This is processing entire events in parallel. Okay, so we proceed to implement this for real, and in a collaboration with the Velo group, we have embedded our cluster finding firmware within the readout firmware of the Velo itself. And so instead of adding an additional FPGA card, we have been able to exploit spare space that was available in the FPGA readout chips that were already there, about a limited fraction actually of an ARIA 10 FPGA. And so it's actually being finalized, and this is a part of the reconstruction. It's actually going to take actual data in the next run. It's in the final stage of commissioning, and we find out that due to the importance of the Velo in the reconstruction, this is actually saves 12% of the load, of the computing load of the GPUs. So effectively allows us to increase the HLT1 throughput in LHCb by about 12% by just using a little bit of spare resources in FPGAs that were there. So this is encouraging, and now we are going to the next step, which is track reconstruction. Of course, this is more difficult. We are going for the moment just to try to do prototypes and not to do a full detector. What we are addressing now is to take the Velo. This is a representation of the layers of the Velo. We chose only to select the layers that participate in the reconstruction of forward tracks that are well within the LHCb acceptance. This is about 38 readout units that actually take the data from these layers. And this is a reasonable amount of information that we can address, but we do need to implement reconstruction in actual cards that we need to add to the system in order to do this. And so we have to build a prototype and only have a part of the system just to show that we can actually do this kind of reconstruction. So, of course, the first step has been to simulate this process. And here you see a nice display of the excitation of these cells, just to let you see visually how this works. So this is the parameter space of tracks, and the color is proportional to the excitation level. So you see these colored spots are the cluster being seen, and the red dots are the actual tracks being generated in the simulation. And so you see that clearly seems to work well. This has been done with the official LHCb simulation, so it's realistic data in realistic conditions. And then you can look and do, quantitative plots and look at efficiencies and reconstruction for various kind of events and various kind of tracks. And again, you find that not only cluster finding, but also track finding, it's possible with this kind of technique with a very good performance, which is very, very little different from what you get from a software reconstruction. So we are now going to the next step, which is to actually build the system. As I said, this time you cannot do this in a single board, so you have to take the extra step of being able to have these boards talk to one another. And so we are working on this connection. We have a plan to connect these 38 cards with 4 or 5 full mesh networks made of fast bidirectional optical links that have a speed that should go up to 28 gigabits per second in both direction. So each subnet, the fully connected subnet, will have some bridges that you see at the periphery of this plot that connect to others with some extra links. And this is actually not too different from the topology that Microsoft used in their Catapult system. It's kind of a similar approach. Again, it's a different speed, but more or less the same idea. And so we already have tests of this system. We know that we can run this with the smaller cards at the reduced speeds, and we are now actually, after performing long duration tests like weeks of operating with the smaller boards, the smaller speed, we are now have initial tests performed with the full speed links at 28 gigabits per second. That's what we plan to use in the final system with the Stratix 10 FPGAs with of the large version, the ones that have 2.8 million of logic elements each. And our outlook now is to be able to operate not the whole thing, but at least one full subnet of order of 8 to 10 cards at full speed, and doing this complete reconstruction over the course of the next year. So to be able to see a prototype that does a significant part of the tracking of the Velo at full speed and see that we actually can achieve this kind of performance. So as I say, this is just a prototype. So where is this aimed? We do have a physics application in mind, but this is more in the phase 2 upgrade. As everybody knows, LHCb is now planning a phase 2 upgrade exceeding 10 to the 34 of luminosity. And the expression of interest that is now being turned into the framework TDR mentioned this R&D towards the realization of a specialized processor for doing reconstruction of downstream tracks in the detector. So these downstream tracks are actually tracks that do not use the Velo. I've been talking about the Velo up to now, but those tracks are also interesting, and they are in using the forward detectors, the so-called T-tracks, and also the silicon detectors in front of the magnet. So the reason of this is that up to now, this is computationally too difficult to be done at level 1, it's only done at level 2. And so by solving this problem, we can actually contribute something that wasn't there before. So it's a little bit more than a prototype, it's actually producing some more data that otherwise wouldn't be there. And it has a large number of applications, because if you can do this, you can also see tracks that are long-lived, that do not decay in the Velo, so you can reconstruct a whole set of things like neutral kaons, lambdas, and you can even look for exotic long-lived particles and so on and so forth. But you also have a number of advantages just in the reconstruction, because having already pre-reconstructed stubs in the forward directions allows you to do more quickly matching with muons or matching with Velo or other kinds of reconstructions that you can more usefully and in a faster way do with using these tools. So there is a detailed proposal in preparation in order to do these kind of things. And just I want to say that we do know from studies that we roughly have what it takes to do this. Clearly, it's a much harder computational problem than the Velo. Otherwise, it would already have been done in other ways. That's the reason we are doing it. But this means that we do have to do something a little bit more complicated. In particular, we have to do this, the plan at least is to do this in 2 steps. So not doing everything one shot, but doing the 4 axial layers first, and then to do the other, the 6 stereo layers afterwards in a second step. So it will be a 2-step process, a little bit more complex, but we still think that this can be done in a very high speed, completely in parallel, except for these 2 steps. And we have studies that show that this is actually feasible, and we have an estimation of the amount of electronics that is needed. And so we estimated that of the order of 150 FPGA cards will be sufficient to do this kind of reconstruction, which is a quite reasonable amount of electronics, especially going more into the future. So this is the current stage. And I just want to mention where this is all heading. In principle, if you are successful in doing this kind of things, you can think of a future where there is a whole set of reconstructions that happens in a layer before doing the event building of the whole event. So the idea is that you can find smaller primitives separately in various detectors by just using this fast local connection. And you can even have a higher and higher integration of these things into the readout. At the moment, we have a tight connection between the readout card and this additional tracking card. But as you have seen, we have been able to do some functions directly in the readout board. So it's possible that it's conceivable in the future you can have a unified board that can do both of the processing at the same time, and then perform this data reduction before going to general reconstruction. So clearly this has advantages, a big project, but you can achieve some reduction of the workload for the HLT, and also possibly some reduction in data flow, which then reflects, of course, in allowing more complex trigger algorithms to be run in the HLT. So allows you more sophisticated things that you can do at the higher level, having in input already pre-digested primitives. So the hope is that this enable higher luminosity. You can have better and larger detectors, possibly with more information, type information, and enable all sorts of more sophisticated things by this mechanism. So to summarize, we have been going through several years of R&D, but we are now close to a real-life demonstration that you can do non-trivial FPGA-based reconstruction at the rate of 30 megahertz. We have detailed simulation studies that show that it's possible to attain good tracking performance if you use a well-parallelized structure and you adopt FPGA systems that are already commercially available. The first step of the Velo reconstruction, that is a cluster finding, is actually already being commissioning for physics application already in run 3, which is in a few months, and has been able to improve in some way the HLT1 throughput essentially for free. So it's very encouraging. And we are now proceeding to studying prototypes of track reconstruction for parasitic use. And this success in doing these things is making us optimistic that it will be possible to have useful contributions with this technology to taking data and doing real-time reconstruction in future applications in interesting kind of fields. That's it for me.
Okay, thank you, Giovanni. It's a very interesting work. We have time for questions. So let's go through people raising their hands first. So Charles.
Thanks, Giovanni. That was very, very interesting. I have a question for you on code portability, because obviously an FPGA is very different from the CPU. And do you have any comments or thoughts on how you could ensure that you have the same results really on the CPU when you're doing simulation in the actual FPGA, or trying to minimize the amount of work that you need to do to maintain two different code paths?
Okay. I'm not sure if you think about having two parallel paths. I mean, the idea is that everything that we run can be simulated in full detail, and actually we have bit by bit simulations of exactly the same things that we run on FPGA. So we can use this and we can verify everything. Of course, when we go to the real application, at some point you run so much data that it's actually impractical to do it in software. That's the reason why you are replacing the FPGA. So beyond a certain point, you'll have to trust the device. But in principle, there is no, nothing prevents you from testing whatever you want until you have enough computing power to simulate all of this. I mean, it's completely simulable. I mean, to the bit level. This is what I want to say. And it's actually been verified.
All right. So there's really no interest in trying to find, like a common language that will produce a different output, or different backends, one for an FPGA and one for a CPU. It's sufficient to understand your FPGA sufficiently that you're happy just using VHDL for it.
Yes. It's not like I mean, it's completely deterministic. Let's say it's not like something. It's not like an analog threshold or something like that. You have no specific control. We understand this completely how it works, and of course you test it. But then it's no different from any other algorithm. I mean, the firmware is just another type of software. It's not like it has different problem from whatever software algorithm you implement in HLT. I mean, it's no different from that.
Right. Okay. Thank you.
Maybe I can quickly jump in with a slightly different answer from the CMS side. That a language, I think, that may answer what you're looking for, Charles, exists, Xilinx Vivado HLS, which is a way that you can write C++ code that then goes through a process where it's transcribed into a VHDL language that's then readable by Vivado to build a bit file or a netlist. And so that in CMS we're trying to exploit, especially for Run 4 Phase 2 upgrade, so that we can have you can run the C++ code by itself and generate an output, and then you run the same code on the FPGA, and you can develop both in parallel. Now, you can't do everything that you want to do on an FPGA with the HLS, and there are limitations to it. It's not as fully optimized as a handcrafted VHDL code, for example. But that option does also exist. So that's something we're exploiting in CMS, and I think Intel have their own version as well.
Cool. Thank you.
Okay. Any other questions from the Zoom? No. Okay. We had one comment on the live notes from Andreas. Did you want to ask that, Andreas?
Yes.
Yep.
Can you hear me?
Yep, got you.
Okay. Recently, I've seen on some very interesting presentation and webinar these devices which combine programmable logic plus vector processors inside, and they are much more complicated than standard FPGA architectures. They seem, to my eyes, to have a great potential, and okay, they are much more complicated. They do involve software programming techniques, as mentioned before. You can do like some kind of embedded C or C++ programming using custom libraries and so on. Maybe people already know this, just summarizing a couple of things. So I don't know. And of course, they do have ARM coprocessors inside, the plus real-time ones. So my thought would be, if you do need accelerated computing, if you do have already an industry paradigm which is very strong, why not use it? Why not think about that? It's a generic question. It's not specific, of course, to CMS or the LHCb. That's my question. My thought. Thank you.
Okay. I may give my comment on that. Okay. So it's clearly there are lots of devices that are being developed, and every year we see new ones. So of course we always have to look at all possible things. However, one thing that I can say about the particular approach that we are using is that by using just the FPGA, they have power, but they also have a very regular structure. So we can design a small module and then repeat it in many copies over the system, and so achieve a lot of computing power by small, let's say, small cells that are very well understood, very well optimized, and then repeat them and tile the chip in this way. And this offers a way that is kind of simple to program, even at the low level, and very easy to understand and very reliable. So that's why we found it, easy to develop things in this way and effective. That's not to say that other ways are not effective, but just saying why we have been we found it, comfortable to work this way. I mean, it's very uniform, very reproducible. But of course, there may be other ways.
Okay. I get the usability thing. Thank you very much.
Okay, thank you. There was just one comment on the live notes about the ACAP presentation link does not seem to be present or working, but we'll follow that up offline with the slides. So if there are no more questions, then thank you again, Giovanni. And we'll move over to the next talk, which is by Thomas James, who's going to tell us about ML inference with FPGA devices for CMS.
Thank you very much. I'm just waiting for mine to stop the screen share, because I can't share the screen while he's currently sharing the screen. It won't let me.
Sorry. Yeah, there we go.
Oh, there we go. Okay, great. Okay. Is it sharing my keynote? You can see that okay? You can hear me okay?
Yep, both okay. So please go ahead.
All right, great. I'll get started. So thank you very much for the opportunity to present today and discuss ML inference acceleration using FPGA devices in the context of CMS. I think this talk is going to be a little bit more general than the previous one on LHCb, which was also very interesting. This one should give a little bit more of a broader overview about what's currently available on the market in terms of the accelerating your ML inference workflows using FPGAs. So firstly, just a little bit about CMS. I'm sure that most people already know. But what is the main problem for CMS computing? It can be summed up by saying big data, right? So CMS, we get a few billion collisions per second. We get crossings, of course, at 40 megahertz. At the moment, it's about 1.5 megabytes per event, which gives us a potential output of about 500 terabits per second. So clearly it's impossible even to read out all that data, let alone process or store it. And so we use a fast trigger, which selects the interesting collisions for analysis, and we throw away the rest. CMS uses a 2-layer trigger system. Level 1, which has a fixed latency of about 3 microseconds. And for this, really, FPGAs are the required device. We also have a higher level trigger, which has a flexible latency, which allocates something like 500 milliseconds of compute time per event. And we're running this on CPUs, and increasingly GPUs are also getting into that game. So this is just an overall schematic, not very detailed, about what the data flow looks like in CMS. So as I mentioned, the raw data that CMS could produce would be on the order of 500 terabits per second. And this is essentially stored in the front-end pipelines of the various subdetectors. And but in fact, only about 7 terabits per second of that data is actually read out to the level 1 trigger at 40 megahertz. And the level 1 trigger has a fixed limited latency time of about 3 microseconds to make that decision on whether the event should be kept or and triggered on, as we say, at an average rate of about 100 kilohertz, level 1 trigger currently, or whether the event should be discarded. And that's simply because that's the amount of time that it can be stored in the front end, that data can be stored in the front end pipelines. So with 100 kilohertz 1 trigger rate, you end up sending about 1.2 terabits per second up to the high level trigger. High level trigger currently has about 25,000 or so cores. As I said, each event is allocated about half a second worth of processing time on those cores. And you end up with about 24 gigabits per second going to the permanent storage. One thing to mention is that if you add up all the FPGAs currently in the CMS service cabinet, I believe it's of the order of 20,000. Many of those are small and quite dated now, so not really comparable to the modern day large chips, but it's just interesting to bear in mind. And it's also worth noting that only a tiny fraction of the data that's actually comes off CMS actually ever reaches CPU. Okay, so FPGA utilization. So I would say that there are 2 broad categories of how one can use FPGAs in the modern world, perhaps 3. So one category, which is the one that's most exploited by CMS, both historically and in the present day, is as a stream processor. And so as a real-time processor, it can process the data with a fixed, no deterministic latency. This is, of course, extremely useful in the context of level 1 trigger. For this, we primarily use custom hardware. I have some examples of some boards that we've developed within CMS, MP7 board, the new Serenity board for phase 2, and US boards CTP7 as well, which are currently running in the CMS trigger system. And we use these form factors that are go in your big crates, in your big racks. They're not the kind of boards that you put into a PC. And so those are like VME for the original CMS DAC and trigger, and now we're currently using micro TCA primarily, and for run 4 phase 2 of CMS we'll be using primarily ATCA, which is this larger form factor you can see with the Serenity board, for example. And with these custom boards, the reason why we need custom boards for this, one of the main reasons is that we need very high I/O bandwidth requirements, and we need a lot of optical inputs. And so typically, I would say the commercial off-the-shelf boards do not have the high level of optical inputs that we typically need for something like the L1 trigger. Now, on the other hand, you can use FPGAs as accelerator cards, so more like you would use a GPU, for example. So usually for the kind of accelerator, you're able to use commercially available hardware. Some examples here, there's the Xilinx LVO series. There's a company called Bitware that makes these sort of off-the-shelf FPGA boards. PCIe form factor is usually used nowadays. They're usually running PCIe Gen 3 or more and more Gen 4. And these boards are available to buy at usually a cost that's higher than GPUs, but they have their specific use cases, which we'll get onto. There's also this area which I call embedded or low power, which is also becoming very popular, where you have these small, cheaper boards that have something like an ARM processor usually, and then FPGA core inside that is programmable. And these are quite good for low power applications, or when you want to be very close to the sensor that's producing the data that you want to process, but it's on a smaller scale than something like that you would need these large, powerful, expensive FPGAs for. Okay, so just a little summary of just really to show the, let's say, the flexibility and diversity of algorithms that we are in CMS running on FPGAs. And here's just a small selection that came up off the top of my head in 30 seconds, basically because there's so much going on that I don't have time to get into today. But already in run 2 of CMS, we've been running clustering algorithms, pattern recognition, energy sums, zero suppression, and boosted decision trees already in run 2 of CMS. Within the trigger and the data acquisition. And for run 3, we're including for the first time deep neural networks, or classic multi-layer perceptrons in the muon trigger, and also Kalman filter algorithms in the muon trigger. And for Run 4, we're already developing algorithms that exploit Hopf transforms and even convolutional neural networks as well. So this is really a growing field, and there's lots of possibilities for potential algorithms to run in your FPGA. Okay, so I mentioned just now a little bit, dropped the name of some neural networks and machine learning applications, and machine learning is becoming more and more exploited across particle physics. One of the major benefits of using machine learning inference is that it allows you to speed up your data processing, i.e. you can train your networks using much more complex algorithms than you would be able to implement at level 1, but on level 1, you're simply doing the inference. And so you gain a lot in terms of latency, you have deterministic latency, and your algorithms are quite scalable. So implementing these, the ML inference within FPGAs allows very low latency, very high bandwidth as well into and out of the FPGA. And then more and more this is needed as particles of interest are very rare amongst the background, of course, at the CMS and at LHC in general. And we need ways to detect them with high efficiency, low fake rates. It becomes more crucial as the pileup increases over the next coming decade. Good. So why use FPGAs as accelerators compared to, for example, the GPU and TPU possibilities? So one way you can summarize FPGAs would be they have the high parallelism that you can get with the GPU, plus a reprogrammable custom architecture. So you can really reprogram and customize your architecture to the problem that you need to solve. And this allows for huge gains in performance for the specific tasks that are best adapted for it. Typically, but not always, of course, the FPGAs are able to achieve a low latency and also improve power efficiency with respect to a GPU solution. But one of the key benefits, which is simply not possible with the GPU, is the bandwidth into the device, and that is really where the FPGAs are key. And an example of this would be in-network processing, where you process data on the fly within the network, and you can have huge throughput there to hundreds of gigabits per second. So some of the workloads that our FPGAs accelerators are used for in industry and in science, you've got, of course, the ML inference, which is taking off in a big way, but you've also got things like video transcoding, database search and analytics, your compression and decompression, your encryption, the computational storage element, which is something like a smart SSD that processes the data or can encrypt or compress the data as it goes in and out of the SSD. And then you've got the financial technology, low latency requirements as well. But as I say, not all workloads are suitable for accelerating with FPGAs. What you really need are sequential or stream-based processing problems where you have predetermined data dependencies and a deterministic execution. You don't want a lot of random accesses. That's going to be a problem. And your host to accelerator transfer overhead has to be a lot less than the processing time, right? And so for this reason, for an accelerator, larger blocks of data are preferred. And just to give a disclaimer, I'll be discussing mostly Xilinx devices just because of my personal experience in CMS. At the moment, we're primarily using Xilinx devices, but of course, Intel devices and others also exist. Okay, so I'm going to give 3 examples of the FPGA accelerator solutions, let's say. The first one is Xilinx LVO. So these are sort of off-the-shelf accelerator boards that you can buy from Xilinx, and they typically contain a 16-nanometer Xilinx UltraScale Plus FPGA, which is the most recent release, except for the Versal, which we discussed just now. These boards usually contain DDR4. You can get up to 64 gigabytes on them, and as I say, PCI Gen 3 or Gen 4. With 8 or 16 lanes, and you've got different solutions depending on your needs, depending on your price, your budget as well. And some of these also contain things like ARM processors built in. They have what's called Smart NIC, so it's got ARM processor built in. It's got Ethernet and everything you need. And then for some of these devices, you can also get high bandwidth memory as well, built in up to 8 gigabytes. There's also what are called Xilinx evaluation boards, which are essentially these, but not branded as nicely. And those still exist and can also be used as accelerators in the CMS. We use those a lot as well. So how does Xilinx LVO work from a workflow point of view? So this is just a little schematic of what it looks like. So inside the LVO itself, you've got the shell, which provides a static functionality that you as a user don't really want to have to worry about, things like the clocking, the links, the configuration, PCIe, status output, and all this kind of low-level control stuff. And then you've got the configurable region of the logic, which runs the kernels, which are then put onto the LVO device from the host. The host has the drivers at the kernel level, and then above that you've got the Xilinx runtime library, which then talks to the board. The Xilinx runtime library implements the sequencing of the kernel execution, allocates the memory, and organizes the transfers between the host and the card. It's used to program the device with the various kernels, either custom made or a list of kernels already exists, and out of the box you can try them. And then you can even wrap the XRT with OpenCL to make it more compatible with your existing software. Okay, so example 2 is something called the HLS for ML suite. This was already discussed or presented in this meeting about 6 months ago by Vladimir Loncha, and I link his slides for more information here. But essentially, just to summarize, the HLS for ML software package translates trained neural networks into synthesizable FPGA firmware. And in fact, it does a lot more than just that. And here you can see in this nice rainbow various steps and where HLS for ML can be used. So you've got your different DL frameworks, your Keras, your PyTorch, etc., and you train your models there. You can then go through a quantization layer where typically you could use something like Keras, where you quantize your model so that it's more efficient when you then put it on the FPGA, ideally without losing performance. The HLS for ML then takes that model and does some optimization, some conversion, profiling, as it also provides profiling and tuning as well, and then outputs your HLS, which is, as we were discussing earlier, it's a language which is essentially C++, and then can be then compiled into a Verilog or VHDL implementation that can run on your hardware. And the HLS for ML even includes support for x86 CPUs as well as Intel and Xilinx FPGAs. So HLS for ML has a lot of upsides. It also has some downsides. So you've got to pick choose wisely whether it's right for your application. So HLS for ML, I would say, excels at very low latency applications, and you'll see that in a moment when I have some results. But it's really excellent at very low latency requirements like the level 1 trigger of CMS, for example. This is primarily because the weights for your neural networks are stored on the chip itself, in the FPGA chip, and so you have very fast access times. But this has a downside of meaning you have a limited capacity. So if you want a very large convolutional neural network, for example, you might not fit. But obviously, the team are working on improving the performance for things like convolutional neural networks as well. HLS for ML allows you to tune the latency with respect to the resource utilization for each layer in your network using a reuse factor. It also allows you to use these very heterogeneous quantization techniques like the Keras that I mentioned, where you can really, every layer, you can choose if you want to use just a few bits for your weights and for your data, or if you want to use many bits. So it's quite, you can optimize really heavily your network for resource utilization and performance there. However, the downsides are that it does rely on the Xilinx HLS, which is a bit of a black box and can often produce non-optimal results. And that is one of the downsides. And then compared to some of the out-of-the-box examples, like the LVO, some of the LVO tools, and my next example, it does require a bit more knowledge of FPGA design than some of the other solutions, but it's still accessible to non-Verilog VHDL experts. Work on support for new backends and also having off-chip weights is ongoing, as I mentioned, but really HLS for ML is ideal for L1 trigger applications, and we expect to use it widely for CMS phase 2 trigger. Okay, so my final example is the Micron Deep Learning Compiler, or MDLA, and this exists in the ecosystem primarily of this board, the SB852, which PCIe board hosts the Xilinx VU9P which is a large Ultrascale Plus FPGA. Also hosts 2 QSFPs, which have up to 28 gigabit links times 4 each. There are a number of other boards that Micron provide, which have lower power as well. This is their largest one, and they provide something they call inference engine, which is a scalable and programmable solution for deep learning inference, and that there is a bit file that runs on your FPGA and is programmable via software. And this provides teramax of performance of compute for your ML workflows. And looks a bit like this. I won't go into too much detail, but it's a hierarchical design where you have multiple compute clusters, each interact with the DDR memory over the soft memory interconnect. And this is quite scalable, so you can add more or fewer of these compute clusters. If you go from a small Zinc 7 chip, for example, up to the largest Vertex Ultrascale Plus devices. This design is optimized for large networks with relatively low batch sizes. And when you do benchmarks with AlexNet, ResNet 50, or Google Net, some of the popular benchmark models, you're able to you have a very high compute efficiency with this architecture of above 95%. So in practice, how this works is you train your neural network model using your favorite Python wrapper, and you have then export your model in a file type called ONNX, which is a sort of a general multi-compatible file type. And this is then fed into the Micron deep learning compiler, which translated to instructions that are then sent to the FPGA firmware and execute your neural network, and then get back your results. And they manage things like the memory, the flow of data, and your models and your weights. And so there's no need for the human to write any HDL or even know how an FPGA works at all, to be honest. You have user-friendly API, reports diagnostics of interest like bandwidth and latency and precision and things like this, throughput. Okay, so those are my 3 examples. And now I'm just going to finally go over a use case, which is something that it's just something that I primarily work on, actually. And it's just one of many use cases in CMS, but this one's quite interesting because I would say it's a hybrid between the accelerator approach and the stream processor approach, and that's something called 40 megahertz scouting. So 40 megahertz scouting in CMS, the idea is to acquire the level 1 trigger data at the full bunch crossing rate of 40 megahertz. So rather than having the full event data after at 100 kilohertz after every trigger, here you're just acquiring the level 1 trigger primitives, which is a subset of the detector information with a limited resolution, but you have the full rate, and that allows for analysis of certain topologies at the full rate, which was before not possible. This concept was demonstrated for the first time at the end of 2018. Again, the last few weeks, we demonstrated it at the LHC test beams. And we're now collecting data from the muon and the calorimeter trigger systems of CMS. And here you can see where the scouting is added into this little schematic, where you're basically taking at 50 gigabits per second the data from the level 1 trigger, and then sending a small, tiny event record to the permanent storage from there. Okay, so we've implemented this SP852 Micron board in the scouting system. So going into the board, you have 10 gigabit per second optical links coming from the L1 trigger of CMS. Within the SP852's FPGA, we run some zero suppression firmware, and then a neural network inference using the MDLA engine. This then goes over PCIe Gen 3 into host PC, where we run a software zero suppression, and then eventually over your network to a RAM disk, which performs another compression, and then eventually goes into your RAID, and then eventually goes into your Lustre file system. So why do we need the ML inference for scouting? What is the objective there? So the trigger objects of CMS that we're collecting and scouting are calibrated for the best efficiency at threshold and for the best trigger performance, not for use in general physics analysis, right? However, we are able to look at, on an event-by-event basis, the full offline RICO and the trigger objects for both zero bias, which is a kind of trigger where you don't have any requirements, which is used for debugging and for testing understanding your system, and then also for triggered events. And we can use these the offline objects as a target when training a neural network in order to correct or improve the parameters that we have from the trigger level objects. We can also use it to reject fake particle candidates. So if let's say you have a fake muon that's reconstructed by the L1 trigger, but offline, you know that's a fake muon, it's not real or it's a duplicate. You can train a network to predict those on the fly as part of your L1 scanning system. So an example, typical example that we've been working with is using the global muon trigger, muon objects, and then training them against offline fully reconstructed muon objects, and we're able to achieve about a factor 2 improvement in the track parameter resolution in the interesting areas of phase space. And so here are some results from using this system with the Micron DLA. So the majority of the latency when using the Micron DLA actually comes from the data/weights transfer between the RAM that's on the board, there's DRAM on the board, and between the FPGA. And so we try to implement a kind of a batching system which reduces this bottleneck. And so as a function of batch size, you can see the latency per inference goes down from about 10 microseconds down to about 5 microseconds with approximately the maximum batch size. It sort of asymptotically tails off here. And this is equivalent to a throughput of about 216 kilohertz per board. So this is sort of within the ballpark of the number of muons from the global muon trigger that we might be expecting to process in LHC-RUN3, for example. And also a key metric is the comparison between the hardware output and the output from the Python or Keras software. And we see that 99% of the time there's less than 1% difference between them. And unfortunately, there is always some small difference when you're comparing the Keras software to the actual hardware implementation. But by doing some tricks like using integer inputs, not using batch normalization, but doing pre-normalization, you can get that number lower. And then there's another example here that we've been working on, which is using a deep neural network autoencoder for anomaly detection within CMS. So the idea here is you have an autoencoder that you train on the standard model QCD background, which then trains to reproduce your input data. Then when you input something to this network that's not a standard model QCD background, it will produce something that is not similar to the input that you gave it. And that this difference can be used as a metric for how anomalous this event is, and could we potentially use this as a way to find anomalous events at CMS. And so we have this model where we input fixed size arrays, including 10 jets, 4 muons, 4 electrons, also your MET of the event coming from the Owen trigger, and then we train it with a QCD background, and then we test it with simulated beyond standard model events and see if it picks up on them. And so far, it's been very successful. We implemented this in 2 ways. So one, using the HLS for ML option with an 8-bit quantization. And second, we're using the Micron DLA, both on the Xilinx U9P. With the HLS for ML option, we have very small latency of only 48 nanoseconds to run the model, the inference. With the MDLA, we got 625 nanosecond latency. MDLA is running at 250 megahertz. The HLS for ML is running at 200. And also using about 20% of the DSPs, but very few, only 8% of the LUTs and very few flip-flops on the device. Whereas the MDLA, because it's a bit file that's provided by a third party, it's using pretty much most of the chip. Okay, so I'll come to the summary. So I hope I've been able to put the point across that FPGAs are really crucial to processing the huge throughput that we have of data at the detectors at the LHC, and that we have been heavily exploiting them in CMS for quite a while. FPGAs can be used as both as stream processors and accelerators as well, and there are a multitude of frameworks available to facilitate the implementation. No longer do you need to have somebody that really can handcraft Verilog or VHDL. Combined with the flexibility and the power of machine learning algorithms, FPGAs can be used to a great effect for both online and semi-online data processing. So that's all. Thank you very much to Maria, especially, for inviting me to give the talk, and my group at the EPCMD and also CERN Open Lab. So yeah, thank you.
Okay, thank you, Thomas. It's a very nice overview of FPGA use, and especially like the number of how many are actually used in CMS. Okay, yeah. So do we have any questions from the room?
Hi, I have a question about the MDLA approach.
Yeah.
You mentioned that it's customized for, it's able to handle the big networks as well, right? I'm not sure how do you get around with the, how is that actually done? How do you fit the big network that is onto the FPGA?
So the board itself has currently we have 64 gigabytes of DDR4 on the board, and this is upgradable actually to 512 gigabytes of DDR4. And so the reason why they can handle big networks versus HLS-RML is because you use this off-chip memory. Now the compromise there is that you have significant overhead, latency overhead in getting the data, for example, your weights to and from your DDR memory. And so that's how it's able to handle the big networks, but also why for small networks, like the example that I gave for the scouting, it has a larger latency than using the HLS-RML solution.
I see. Okay.
Thanks.
Okay, Giovanni?
Yes, okay. Yeah, first, just let me make a general comment that this was very interesting for me to see that essentially the same feature that we found, the features that we found useful are essentially the same. So we appreciate the same things for the very similar reasons from different ends. So that was interesting for me to see. But I also have a question about, I think it was around the slide 19 about your latencies.
Yep.
When you say you have a batch size of 4,000 and then you do latency of 4 microseconds, I guess you mean latency per event. I mean, the actual latency, 4,000 events must be about 100 microseconds just to get them. Could you explain?
Exactly. So this number is the average latency per inference.
Per event.
So, per inference.
Per inference. What do you mean by inference? Maybe
one inference would be you take one vector of data and you output one vector of data. So whether that's a single muon that you want to correct its parameters, or whether that's a whole event that you want to output some value, some score, whether it's anomalous or not, right? That would be one inference in this case. In this example, where one inference is one muon. So we input one muon and we perform one inference to say, okay, here's the output, here's the corrected muon parameters.
So how many do you do? So a single event, how, I was just trying to figure out.
Yeah, so on average, we have less than one muon per event.
Okay.
So yeah, it's maybe half a muon per event on average.
But the actual event comes after 4,000, so you have to batch them, and then they come
up. Yeah, so we store
microseconds later.
We store the 4,000 in the block RAM on the FPGA, and then we send that in one go to the DRAM.
But so this is not level 1, just to understand, because level 1 you say to have to do in 3 microseconds. Of course, this cannot be level 1.
Yeah, so this is where it's a hybrid, where we're taking the level 1 data, but we don't have the strict latency constraint that you have on level 1, because this information is never used to trigger CMS. It's simply used for analysis, for a semi-online analysis, right? So that you don't have to get that result before the front end buffers fill of CMS, right? But you still have your limitation. Then becomes the main metric that you care about is your throughput, right? Because you still have to keep up with the input data rate. But if you how long you need to buffer is acceptable, because you don't need to actually use it for triggering. That helps?
No, thank you. It's just to clarify, because I'm trying to, of course, map this into what we do. We actually never do, for instance, I didn't mention this. So we don't do any batching. We actually found that we can work with data flow, just data comes in and comes out. And we have a total latency, which is below a microsecond to do the whole thing. I mean, that's more or less what we get. But we don't do any batch processing, okay? It's well, it may not be so relevant, because I understand what you do is just it's just a delay, and then you still process the whole rate, if I understand. But
yeah, it's just a buffer. It's just a buffer inside the chip where you store your data until you get a block that's big enough to make it worthwhile to do the transfer. And then,
okay. Yeah, just to clarify the difference between what we do and what you do. Okay.
Yeah,
okay.
totally. Thanks.
Okay, any other questions? See anything on the live notes? Actually, so just one from me on the what was it? The Micron Deep Learning compiler. So that is a proprietary PCI, FPGA, or is this something that will eventually be supported generally on other devices? You know, going via this ONNX format through a compiler directly to HDL.
Yeah, so the Micron Deep Learning compiler is currently only for the boards that are developed by Micron. Actually, there was a startup that they purchased that developed these boards and the compiler. And so currently that's only, you need the hardware and you get the software with the hardware kind of thing. The bit file, the bit file that goes on the FPGA, which is runs their their inference engine, is not publicly viewable, let's say. They provide really just the bit file. You don't get the source code. For the compiler, you have the source code, and the driver is part of like the driver and the full suite of software that comes with the board. In the future, the next steps in fact are that they're developing an ASIC, which will, I think, eventually become their main product, because the performance gains that you can get from putting this in an ASIC are high, but obviously you lose some of the flexibility. So at the moment, it's quite nice. You can buy these boards and you can put your own firmware on it, but you can also use their accelerator. So that's why I'm able to run the HLS for ML and then also run the Micron Deep Learning compiler on the same piece of hardware. Yeah, at the moment you need the same. It's the hardware and the software come together at the moment, unfortunately.
Oh, okay, thanks.
Thank you.
Okay, any other questions? Oh, we have something for Bruno. Do you want to ask yours? Question from the live notes.
Yeah, sure. I hope you can hear me.
Oh, could you raise your volume a bit, please?
Yeah, that's the issue. Is it better now?
That's better, yeah.
Okay, so I was just wondering, the outlier detection algorithm, what's the percentage of fakes that you get, more or less?
Yeah, so that's a good question. So it's quite it would take quite a bit of time to explain the full details of the anomaly detection algorithm. So what I will do is I will add a link to the latest presentation, and there's I think something is also on the archive now, with an overview of the work that was done here, and I'll add that to the slide and then re-upload the slides on the Indico agenda, because you can't. It's not like you can really give a fake rate. It's more about you choose your you would choose your acceptable fake rate, and then the question is how much boosted is your signal? How much is your signal boosted? Because the signal is going to be extremely rare. So it's all about boosting your signal with respect to the fake rate. So there's many working points that you can look at. But what I'll do, I'll put the link to some material on the slides, where we put them on the Indico, and that should be that's your place to look, because yeah, we don't really have time to go into all the details right now.
Okay, sure, thanks.
Thanks.
Okay, any other questions or comments? No, okay. Well, thank you again to our speakers for two very interesting talks, and for all of you for connecting and for the discussion. The live notes are obviously online on the agenda if anyone else wants to comment or add any links. So with that said, thank you again all for connecting, and we'll hopefully see you again at the meeting on Wednesday, the 8th of December. So the meeting is closed, and thank you everyone. Have a good day.
Thanks again. Bye-bye.
Thank you, everyone.
Thank you.
Bye-bye.
Bye.